Hello, I'm Richard from Dartmouth College. I'm here to present our paper, Predicting Three-Pointer Landing Poses in VR using Multimodal LSTM-Based Neural Networks. This work was collaborated with Yushi, Xuning, Wolfgang Stuerzlinger, Yuntao, Wang, and Hai-Ning Liang. Virtual reality enables highly immersive experience, but effective interaction is the key. One of the most fundamental interaction is the target selection. Raycasting with controllers or bare hand is common, but it struggles with small, distant, or occluded targets, leading to frustrations and inefficiency. To improve raycasting, researchers explore various enhancements, including visualizations, heuristics, and behavioral adjustment. Some approaches leverage predicting methods. For instance, predicting hand movements to enhance detection, using gaze endpoint distribution to resolve selection in dense environments, and more recently, employing biomechanical simulation to generate training data for neural networks. Henriksen's head-coupled kinematic template matching, or HCKDM, introduced a new approach to predicting target selection. By analyzing cursor trajectories and matching them to predict motion templates, it can accurately predict landing positions without additional input. While effective, this method still relies on predefined templates and manual matching. We believe a learning-based approach can achieve the same goal more efficiently by directly modeling human position behavior. Additionally, HDKDM benefits from incorporating head rotation, but we see further potential integrating gaze data since humans naturally look at target before reaching for it. Gaze could provide even stronger predictive signals for selection accuracy. Our approach augments this prediction method in several key ways. First, we replace the kinematic method with a neural network. Secondly, we incorporate eye tracking data as input modality. Finally, our model is participant independent. What we found through our study is that through these changes, our model increased prediction accuracy by a factor of 3.5 and 1.9 respectively, when 40% of the way through the movement. Additionally, the participant's independent model also demonstrated accurate prediction compared with user-specific model. Before introducing our LSTM model, let's first look at the HCKDM. This method works by matching a user's motion to a library of pre-recorded velocity profiles. It captures four types of velocity data: headset and controller, both angular and linear. When a new selection begins, the system compares velocity to the templates by calculating the difference at each time step. This process is repeated for all four velocity types, generating a similarity score. The system then selects the best matching templates and computes the weighted average of their movements. This predicted motion is applied to the selection starting point, adjusting its direction based on prior movement patterns. Our approach collects motion data from the HMD, gaze, and hand, extracting velocity and movement amplitude at each timestamp t. Since trial duration vary, we use post-padding to align all sequences with longest trial. To help our model recognize partial sequences, we segment and augment the data. The model is trained to predict two key values: the travel distance and rotation angle. These predictions are then applied to the selection starting point, adjusting direction or angle accordingly. Two user studies were collected in this work. The first used to collect user data, analyze the behavior of each modality, and identify the best input modalities. The second study compared its performance with current state-of-the-art model in terms of accuracy and generalizability. In both studies, participants performed reciprocal pointing tasks in VR. They are required to repeatedly select between start target and end target using hand ray pointer. The setup can be seen in the clip being shown. Predictions were not shown during either experiments. In our first study, we focused on selecting the best input modality by varying key parameters, such as the depth of the start and end targets, the angular distance between them, their position around the user, and their width. This helps us collect data across different task difficulties. We tested three depth conditions, 60 angles for pairs of positions, and two width conditions for the target. Each participant performed 4 repetitions for each condition, which resulted in 3,456 trials per participant. In total, we gathered data from 16 participants, leading to over 55,000 trials. We observed many interesting results, but here I will focus on the results regarding with the gaze feature and model performance. The first, we discovered that gaze provides an earlier signal of user intent than either hand and HDMD movement. This timeline represents the progress of a pointing movement. The vertical lines indicate when, on average, each modality reaches peak velocity. As you can see, gaze velocity peaks significantly earlier at around 40% of the movement duration compared to HMD and hand. Final gaze ends about 46 of the progress. It gives us a head start in predicting the user's intended target. To evaluate the contribution of each modality, we trained and tested our LSTM and the HDKDM models with various input combinations, single modalities or possible dual modality combinations as train modality input. To compare the results for different models, we adopt two consistent matrices to compare the results. First is angular distance, another is the target hit rate. The right graph shows the prediction accuracy of our LSTM model with different input conditions across the entire task. The best performance is achieved when all three modalities, gaze, hand, and HMD, are combined. We also tested if incorporating eye gaze data could enhance accuracy of the template matching technique, shown in the left graph. Interestingly, models using gaze alone performed worse, particularly in the early stages, even trailing behind the HMD-only model. This is likely because gaze movements are fast, and the velocity difference are minimal in the initial ballistic phase, making it harder for KTM approach to match the templates effectively. In contrast, KTM work best during the later correcting phase. This comparison also served as initial test bed for our model and the KTM model. At the 40% task progress mark, our model's worst performing input, 9.29 degrees, still outperformed the best performing input of the KTM model, which is 12.49 degrees. To validate the model more thoroughly and test its generalizability, we ran the second study. First, to make the experiment more practical, we use a continuous range for parameter. Second, we compare the performance with multiple methods, including HCKDM, LSTM, and the non-prediction baseline. Finally, we test whether our model can predict well on new users. Here shows the parameter used for our study 2. Basically, it's similar to study 1, except we use a continuous range for theta. The rest of the variable were randomly distributed between the values we used in study 1, as shown on the slides. For this experiment, we broke the session into 50 blocks, each with 7 pairs of targets covering all angles in random order, and the user was required to perform 6 selections. This worked out to 2,100 trials per participant. From the original pool of 16 participants, a total number of 8 participants completes this experiment. We collected 16,800 trials in total. In this study, when compared the performance of our LSTM model with optimal input to the HDKD model, using the angular discrepancy between the actual trajectory and the target result prediction as a baseline, we found that LSTM model outperformed HDKDM from the very beginning of the task. As shown in this graph, our model achieved angular accuracy of 7.06 degrees compared to 13.28 degrees for HDKDM and 24.77 degrees for the baseline. This represents an improvement about 1.9 times over HDKDM. Additionally, unlike previous methods that become less accurate towards the end of the movement, our method maintained higher accuracy even at the final stage. Regarding target hit rate, our method consistently outperformed HDKDM model between 15% and 90% of task progression. We also test the generalizability of one model by training it on data from multiple participants, aiming to create a model that works across users without requiring individual data collection. We train on data from 6 random participants and test on data from 2 others. At 40% of the movement, the model achieved angular accuracy of 9.97 degrees, which is nearly identical to the 9.50 degree accuracy when using data from individual participants. We also conducted cross-participant experiments, where models trained on each participant data were used to predict the data of either other participant. Generally, the model achieved the best result for each user with models trained on their own data. In real-world scenario, we still recommend using models trained with participant split data or use several users' data to achieve general participant model. Now let's discuss the broader implications of this work and the potential directions for future research. By adopting neural networks, we can focus entirely on data input, making it easier to extend input modality without the need for manual parameter tuning, as required in template matching methods. Additionally, since gaze naturally precedes head and hand movements, it provides a more informative signal for target selection. When integrating such systems into real-world applications, 2 key factors need to be considered. First, detecting the onset of selection behavior is crucial, as it determines when to begin processing the input data. Second, the timing of predictions play a critical role. Predicting too early may lead to inaccuracy, while predicting too late means the user is already near the target. Based on our observation, making predictions around 40% into the selection process could be a reasonable balance. Our system has several promising applications. One is integrating with facilitation techniques. When the model outputs a high-confidence prediction, the cursor-control display ratio can be dynamically adjusted near the target to reduce refinement time. Another key application is reducing system latency. In VR, resource-intensive processes like memory allocation and rendering can cause delays. By leveraging prediction, the system can proactively process data or rendering relevant areas before the user makes a final selection, improving overall responsiveness. Let's conclude the brief summary of our work. We developed a novel multimodal LSTM-based model to predict user ray-pointer landing poses, leveraging complementary information from hand HMD and gaze movements. Our approach significantly outperforms existing methods. This work represents a significant step towards creating more natural, responsive, and seamless target selection experience in virtual reality. Thanks for listening. For more details, please refer to our paper.